the plane meets a paraboloid, we get this circle, y squared plus z squared is equal to 1, and that gives us a region D over which we'll evaluate a double integral. Now, we would need to come up with limits. So if we look at our circle in the yz plane, and we want to come up with limits of integration, let's say we want to come up with limits in terms of y, and then limits in terms of z. So here we have y squared plus z squared is equal to 1. So what should limits in y and z be?
I mean, if that's just a unit circle, should they both just be -1 to 1?
Well, you would pick one of them to be
Right.
negative 1 to 1. All right, let's say we pick y to be negative 1 to 1. All right, and we still have 4x squared plus y squared plus z squared to 4 for our innermost integral. So our outermost integral is dy. And now we need to pick limits on z for each value of y between -1 and 1. So what should the limits in z be? Given that y and z satisfy y squared plus z squared is equal to 1 on the boundary, so we want to go from what? Yes, that's your upper limit. Yeah. So then, well, we just do negative. Yeah. So minus square root of 1 minus y squared up to plus square root of 1 minus y squared. And that is, so now we have our integral completely defined. Now, that should be a y. Okay, so then we can go ahead and evaluate that. But this can be kind of a pain to do it this way, especially once we do this inner integral. That's not much of a problem. But then we have to end up differentiate again, substituting these limits, and then dread the result of that to evaluate something over here. There is another way we could do this. Another way we could handle this region D. What can we do instead of this? That we've talked about recently.
To make z from -1 to 1 and y?
That would really, yeah. But something a little more radical than that.
Panic?
What?
Panic?
No. Alright, so now we're back in the land of double integrals here. So, the kind of what?
Some kind of like gradient of like the change.
No. What? Polar coordinates. Yes. Yeah, so in this case we can define y is r sine theta, z is, actually, here we have cosine, and z is r sine theta. So now we have the equivalent of a polar rectangle. So r goes between 0 and 1, and theta, we go all the way around the circle. So theta goes from 0 to 2 pi. So now we have limits that are constants. So now we can write this integral as, so this can instead be written as integral from 0 to 1 in r, 0 to 2 pi in theta, same limits for the innermost integral, but instead of y plus z squared, what will I have? Not r, r squared. Yeah, so for r squared, we still have x, that doesn't change, so dx, and then we have dr, actually that's d theta for the integral, and then dr, and what did I forget?
R.
R, yes, still have to put the r in there. Yeah, and there you have it. So now you can integrate that relatively harmless integral. No square roots to be concerned about. Okay, so after you work out one of these variables, if what you're left with is a double integral over a circle, or even something that can be viewed as a polar rectangle, you might find it more convenient to switch to polar coordinates to avoid having something dreadful to try to anti-differentiate. Yes?
It says z equals zr sine theta.
Oh, that should just be r sine theta. Yeah. So I chose it because y was playing the role of x. I really could have done either one in this case.
Yeah. I think our class is shrinking.
Well, we did have a drop deadline yesterday.
Yeah, I'm not here.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, there was 12 here in this room, but there are 19 enrolled.
Oh, God. That's not good for science.
Maybe I'm gonna make it some business.
Well, this is what I get for not counting attendance and for putting everything on the site and then you putting everything on video. And so, yeah, I see it coming.
Oh, well.
Yep. Yeah. So let's not forget the Floyd factor.